Hi everybody, welcome to this section. In this section I'll discuss about the SIMULINK and how do we do the simulation. So let's begin with it. You will go on MATLAB, you will open MATLAB and you will just you will write down SIMULINK in comment window. Then press OK, it will come over and you can see we'll start it from zero, from scratch, so to build our models. Let's start from here. You click on here, this plus sign, and it will be open. New. Yes, as you can see. So let's name it to register. Save as. Let's call it YouTube. Yep. Okay, no problem, already exists. So let's say YouTube 1. Okay, YouTube 1. Yeah, it'd be great. Then after you come up, okay, so to make the visions, in the last section we discussed about the Newton's second law and Kirchhoff's voltage law about the motor position controlling. So in this SIMULINK we'll draw these equations. We'll start from mechanical system first in Newton's second law, then after we'll go for the second part, which is electrical, Kirchhoff's voltage law. So for the mechanical part, we can see there is theta double dot, there is theta dot, so which is correspond to accelerations, and the speed is theta dot. So the position will be theta, which is our angular position. The motor position will determine our angular position. So in terms of transfer function, theta double dot is we need two integrator to have theta double dot. So let's go to SIMULINK library, and we'll come back to common use block. In common use block we can have an integrator here, just drag and drop in our SIMULINK. There we go, you drop it here. To make a copy, just right click on it and it will make a copy. So we need double. Let's call this one, as I said, theta double dot. Okay, as you see here, and let's call this one theta dot as our position, speed, I'm sorry. Theta, speed. Okay, theta dot here. And here is acceleration. I will just make abbreviation. X is our acceleration. And there is a position, angular position, so let's say that's theta correspond to our angular position, so we'll just do it like this, and yeah, there we go. And we need an output. We need a scope to see our output signal, to see the system performance about the position. So let's try to check for a scope in SIMULINK library. We can't see here. Let's come over to sync. We will have a scope for observation. Drag and drop in here. Yep, this is our scoop, and connect them together. Yeah, and after, you see here we have 2 theta double dot. Then now the theta double dot is multiplied by g over 1 over j, which is proportional to our coefficient acceleration. So let's 1 over j, and let's rearrange it a little bit to make it pretty good. Okay, yes, as I said, this is like our mechanical part. So let's check our, now we see that the theta dot is being multiplied by b minus b, so we need a gain again to multiply theta dot with b, which will come back to add to some part here. So we need a sum part. So let's come to Simulink library and go to common use block and summation to use, check, yes, drag and drop summation or control+I will just do it for you. And you can see here, so this summation, okay, I'll make a copy for b viscous coefficient, and to flip a block we need to just press control+R, or maybe right click on it. Yes, right click, then you will see flip, rotation, control+R did it for you. So I'm going to use control+R, which is faster. And now for the speed side, okay, I connect it, and this is our viscous coefficient. So we'll connect this viscous coefficient to the summation block. Then after, let's see again what we left. Okay, I think it's almost done for the mechanical parts. So let's begin with the electrical parts. As you can see, di by dt, so we just need one integral for transfer function. So let's just make a drag and drop for the current. So this part is going to be our current, di by dt, di by dt. As you see, I'll call it current so you can understand. And when you take a look again, you see that the current is being multiplied by R, which is resistance, our resistance. So we need a gain for this, and we see there is 3 summation here. So let's have a summation block with sign and drag and drop here again, and you connect this one. Then after we need one more gain for the resistor. Let's just try to flip it so you can see, rotate. Yes, there we go. I think now you're familiar with rotations and flipping. And I'll rename this one for resistance. Double click on it. Yes, I'll put minus R, or I can put R directly, in case it depends on you. Whatever you like, if you like, you can make positive feedback. If you like, you can make negative feedback. So I'm going to change this one to 3 sign, minus plus minus. For feedbacks, I'll use positive feedback. Let me just take this one out from here and put it right here. Yeah, there we go. Rearrange it, and after, let's look at it, what else we need. When you look carefully, we see that there is KT, which is in mechanical side, but also take part from the current, which is electrical side. So we need a gain that will be connected to the current di by dt. So let's just grab this one, make copy. I'll name this one to kt, which is our torque constant value, and that one will be connected to the current I, as I showed you earlier. And we'll go to the mechanical part to sum it. So what else we need? When you look careful again, you see that there is electromotive force constant kb, which is represents kb, but in electrical size, which take part in also as a mechanical part. As you see, electromotive force, it is in electrical side here, so we need one more gain. So let's just multiply this one, copy this, let me flip it. Yeah, that was okay. So this is gonna be our kb, which is back EFM constant, MF. Let's change it, kb, yes. Then it take part from theta dot, as you see. I hope you are not confused now, and come to, it was negative, I think, so you can look at it again. Yes, minus, so I will give it to minus, as you see, negative feedback, and it was multiplied by theta dots, as you see, theta dots. So this is the line. I will just rearrange it so you can see it clearly. Yes. Okay. Take this one here. Make sure this is correct. Yeah, I think you can see it easily now. Yep. And I'll remove this one a little bit. Yes, I think now it's perfect, so you can see clearly. Then after what we left, I think you almost describe everything here. Just we need a voltage supply, so V. Let's go to common use block in SIMULINK library and select source for a step. Okay, you see, you just come to source and you find a step or any kind of input value. So I will take a step input, drag and drop, or if you like can make control+I, that will drop it for you. There we go. Come back with it. Yes, okay. And as you see here, this box is very important because it is the connection between electrical system and mechanical system. So we in electromechanic, we sometimes call this one as well gearbox, which is the connection which connect the mechanical system to electrical system. Gearbox, kind of transfer function, transfer between electrical and mechanical. Yes, so I think everything is okay now. So let's just name this one voltage. Then after in order to run this one, we need a MATLAB M script file. So I already did an example. Let me show you. Here, you can see this is the viscous coefficient constant, and this is the moment of inertia. This is our KB and KT. Let's look carefully if we messed up something. when you look carefully, I forgot to miss the 1 over L, so that place is here, it should be here, so we need to cut this one and put a bar here. Again, just flip it and rename it 1 over L, which is inductance value, and connect it here. There we go. Then everything is okay now. Yep, I think everything is okay. L value is here, R is here, V is here, KB is here, DT are also here, theta dot, as you see, B also is here. Yes, everything is okay. Let's see. Okay, this part is moment. This part is the M script. Like I said, B, which is equal to viscous coefficient. I just give a random example. You can, I will put the access of this example link, so you can also have access on it if you want it. And this KT is our motor torque constant, KB is motor back FEM constant, which is with units is in volt radian per second. This is the voltage, resistance, and inductance. And sim, this is a function that does automatic simulation for you. It's just run your Simulink without going to the Simulink block. It just do it here automatically. Okay, let's try to, and for the YouTube too, so you just register the name of your Simulink, as you see here, YouTube 2, and come back here and just write, copy paste that name, then you will just see. Let's try to give it run. Let's run it to see what happened. Yep, it's busy, so that means everything is okay so far. Let's go and check it if it's running. Yes, it's running. Yeah, exactly. So you just look at the scope, what is happening here. So in order to see the angular position, you look at the scope. Yep, as you see, it's raising. Good. But we see that the system performance is not good enough, so we want the system to perform in good way. So in order to do that, we need to use another controller, which is PID. So we'll use the system with the PID controller in order to make a good output of signal, as you see. So in next video, I hope to see you. I will continue with the PID, just change to implement some modifications. All right, have a good moment. Thank you.